Hi everybody. So in this video, we're going to look at the sum of complex series, and we're going to be using the various trigonometric identity using De Moivre's theorem. So we'll work through 3 exam-style questions, and if you want to work along with me, you can download this PDF from my website. So if we begin with this question, we have this complex geometric series, and we can see it's geometric because there's a common ratio, where we multiply every term by e to the I theta, all the way up to the 10th term. So because it's a geometric series, we can use the standard formula where the sum of the first n terms be a, the first term, multiplied by 1 minus r, the common ratio, to the power of n, the number of terms, over 1 minus r. And we can see that a, the first term, is this one, e to the I theta. R is the same. This is the common ratio. And n equals 10. So we can substitute each of these into our equation. So the sum of the first n terms will be e to the I theta multiplied by 1 minus r to the power of 10. And when you raise this to the power of 10, we get 10I theta using the power rule over 1 minus r. Okay? Then you can see in the question, we need the denominator to be in the form of sine. So we can use the identity where we have z to the n minus 1 over z to the n will equal 2i sine n theta. And the special case when n equals 1, and this becomes 2i sine theta. Okay? So we're going to need to use these to make this summation look like what we have here. So the way we go about this is we need to multiply this fraction by e to the negative 1/2 I theta. And we do it to a numerator as well, so the fraction remains balanced. Because what will happen, when you multiply this term by the 1, we get the negative half power. And when you multiply it by this term, we get the power of 1, take away the half, we get the positive half power, which leaves the denominator in this form, where the n would be a half. So if we multiply these out, we've got e to the I theta multiplied by e to the negative 1/2 I theta times 1 minus e to the 10 I theta, all divided by this term minus this term. And because the bases are the same, we can just add the powers, and we get e to the positive 1/2 I theta. But now we have a new problem in that you can see the one with the positive power should be the positive, but this is a negative. So what we need to do now is to multiply the fraction by negative 1. And we can also use the addition rule of indices to add these two together. So we'll get e to the 1/2 I theta. This is just the 1 take away the half, multiplied by, when you multiply this by negative 1, this term becomes positive, and the 1 becomes negative. So e to the 10 I theta minus the 1 over, and when you multiply this by negative 1, this term becomes positive, and this one becomes negative. So e to the 1/2 I theta minus e to the negative 1/2 I theta. And now we have it in this form where the n is the 1/2. So we can substitute this into our denominator. We'll have e to the 1/2 I theta multiplied by e to the 10 I theta minus 1 over the 2i sine n, which is 1/2 theta. Okay? And this is what we were asked to show here. In the next question, we're going to take this a little bit further by looking at a convergent series. So in this question, we've been given a convergent infinite series defined by a and b, where a is this expansion and b is given here. We need to show that a plus ib can be simplified to this. So if we begin, we'll just say that a plus ib, well, the a terms will be all of these. And then we'll plus the I multiplied by all the b terms. And the b terms is all of these. So now we need to expand out these I terms, and then we can collect together the theta terms, the 2 theta and the 3 theta terms. So a plus ib will be the 1 plus, and what we can also do is factor out this half. So we'll get 1/2 of cos theta plus I sine theta. So I've collected these theta terms together and I've factored out the half. We can do the same for the 2 theta terms. We'll factor out this quarter and we'll collect together the 2 theta terms. We'll do the same for the 1/8. We'll factor this out and we'll collect these two together. And this series will go on infinitely. Now we can simplify this because we can write these complex numbers in exponential form. So we'll have a plus ib will be 1 plus 1/2 e to the I theta, which is this term, plus 1/4 e to the 2I theta, plus 1/8 e to the 3I theta. And can you see that this appears much simpler than what we have here? And again, this goes on infinitely. So now we've got a geometric series where the common ratio is 1/2 e to the I theta. If we multiply the half by a half, we get the quarter. And when we multiply this by e to the I theta, we get e to the 2I theta. So we have a common ratio of 1/2 e to the I theta, an initial term of 1, and we're looking at a infinite series. So we can use the standard formula when this is a over 1 minus r. So we can write a plus ib as a, which is 1, over 1 minus the r term. And then we can simplify this. If we multiply top and bottom by 2, it will cancel out the 1/2. This will give us 2 over 2 minus e to the I theta. And this is what we were asked to show here. And now for part B, we need to show that this is the real part of a plus ib. And you can see this denominator now has a cos term. So we're going to use the identity where z to the n plus 1 over z to the n will equal 2 cos n theta. Or when n is 1, z plus 1 over z is equal to 2 cos theta. So this means we need to convert this denominator into this form. So we need a negative power of e. This will give us this term. And the way we get this is we multiply both numerator and denominator by 2 minus e to the negative I theta. And by multiplying it to both, the fraction remains balanced. So what will happen, when we multiply this term out, we'll get the positive I theta, and when we multiply this term out, we'll get a negative I theta. So this will give us this form. So if we expand these out, we'll get the 2 times 2 to make the 4, and then the 2 times the exponential term will give us minus 2e to the negative I theta over, we'll have the 2 times the 2, this will give us 4, the 2 times the exponential term with a negative power, so minus 2e to the negative I theta. This term multiplied by the positive 2, so then we get with positive power, and then we get this term multiplied by this one. So the negative times a negative will give us a positive, and when we add these two powers, because the bases are the same, this will just make e to the 0, or just 1, and positive 1. So now we can tidy this up. We can add the 4 and the 1 together, and then we can factor out the negative 2. So we've got 4 minus 2 e to the negative I theta over the 5, and then negative 2 multiplied by, I'm going to write this term first, so it's in this form, so e to the I theta, and then because we factored out the negative 2, this is going to be a positive, so plus e to the negative I theta, okay? So the key to this question was realizing to multiply this fraction by 2 minus e to a negative I theta, because we wanted it to look in this form. So now we can just expand out this bracket. So we'll get a plus ib will be 4 minus 2e to the negative I theta over 5 minus 2 lots of 2 cos theta, okay? So I've just replaced this with what we have here when n is 1. Then we'll expand out this bracket, and I'll convert this to modulus argument form. So we'll have 4 minus 2 cos, and because this is a negative theta, the argument will be negative. I'll change this to a square bracket, plus I sine negative theta. And then this is divided by the 5 minus 4 cos theta. Now, if we look back to what we're trying to show, we've got positive theta. So we need to convert this negative into a positive. And we can use the properties of the sine and cosine graph. So we'll get a 4 minus the 2 cos theta. Then this becomes a positive, and then the positive I becomes negative, but the argument becomes positive. And when you multiply this negative by this negative, it becomes positive 2i sine theta, okay? All divided by 5 minus 4 cos theta. So now we've got it involving sine and cos, we can equate the real parts. This a term will have these real parts, all divided by this denominator, and the IB term will have these imaginary parts, again divided by the same denominator. So A will equal 4 minus 2 cos theta over 5 minus 4 cos theta, and B, or IB, will equal 2i sine theta over the same denominator. And then we can cancel out the i's, so these will go. So B will be 2 sine theta over 5 minus 4 cos theta, okay? So this is our real part, and this is our imaginary part. Let's try one more question. So we've been given another convergent infinite series defined by a and b. These are the a terms and the b terms. We've been asked to show that a plus ib can be written in this form. So do you want to give this question a go? You can pause the video and come back when you're ready. Okay, so welcome back if you had a go. How did you get on with that? If we say that a plus ib, and these are our a terms, so we'll have a cos theta plus 1/3 cos 3 theta and 1/9 cos 5 theta plus I multiplied by these b terms, then what we can do is we can expand out the bracket with the I, and we'll collect together the theta terms and the 3 theta terms and the 5 theta terms. So a plus ib will be cos theta plus I sine theta. Neither of the terms are highlighted in blue. Plus, and we can factor out this 1/3. Lots of cos 3 theta plus I sine 3 theta. Neither of the terms are highlighted in orange. And plus 1/9 of cos 5 theta plus I sine 5 theta. And these were the ones in green. So now we can replace each of these modulus argument forms with an exponential form. So a plus ib, e to the I theta plus 1/3 e to the 3I theta plus 1/9 e to the 5I theta. And we're told that this is an infinite series. And we can see this is geometric because the common ratio is going to be multiplied by 1/3 of e to the 2I theta. So if we use the sum of a convergent infinite series as a over 1 minus r, then we know the a term is this first term, e to the I theta, and we know that r is the common ratio of 1/3 e to the 2I theta. So we'll substitute each of these into here. So a plus ib will be the a term over 1 minus the r term. And then we can make this look like what we have here by multiplying both the numerator and denominator by 3. So we'll get a plus ib is 3e to the I theta over 3 minus e to the 2I theta. Okay? And that's what we were asked to show. Then for part B, because we need a denominator of 5 minus 3 cos 2 theta, we need to use the trigonometric identity where z to the n plus 1 over z to the n is 2 cos n theta. And the special case when n is 1, z plus 1 over z will equal 2 cos 1 theta. So we need to make this denominator appear in this form. So the way we're doing this, we multiply both by 3 minus e to the negative 2I theta. Because what will happen, we'll have the 3 times this term to give us our negative power, and this 3 times this term to give us our positive power. So when we expand out the numerator, we'll get 9e to the I theta, and then multiply by this one will give us negative 3 e, and we'll add these two powers, and we get negative I theta divided by the 3 times the 3 to give us 9, the 3 times this term to give us our negative power. This will give us our positive power, and then when we multiply this by this one, we'll add the powers, so we'll get e to the 0, and the two negatives will make a positive, so we get positive 1. And then we can tidy this up. We can add the constants together, and then factor out the negative 3. So if I just move this over to here, we'll get 9e to the I theta minus 3e to the negative I theta over the 10 minus 3. And I'm going to write this positive power first, because you can see that's where it goes. E to the 2I theta plus e to the negative 2I theta. Okay? And now we can replace this term with 2 cos 2 theta, and we can expand out each of these in modulus argument form. So we'll get a plus ib will be 9 times the cos of theta plus I sine theta, which is this term here, minus 3 times the cos of, put this in square brackets, negative theta, if you see this negative, plus I sine negative theta, all over the 10 minus 3 times 2 cos 2 theta. Then what we can do here, using the properties of the cos and the sine graph, we can write this as cos of positive theta and then minus the sine of positive theta. And we can expand out each of these brackets. So now we'll get 9 cos theta plus 9i sine theta. We know this becomes cos theta. When we times that by negative 3, we get negative 3 cos theta. This becomes negative I sine positive theta. When you multiply that out by the negative 3, we get the positive 3i sine theta. And then for our denominator, we've got 10 minus 6 cos 2 theta. And we can tidy up our numerator. We can collect the cos term together and the I sine terms together. So now we'll get the 6 cos theta plus the 12 I sine theta, all divided by the 10 minus 6 cos 2 theta. And then we can factor out the 2 from each of these. So this will simplify to 3 cos theta plus 6i sine theta over the 5 minus 3 cos 2 theta. Now we need to identify the real and the imaginary parts. We know the A term will be the real part and the B term will be the imaginary part. So A will equal 3 cos theta over 5 minus 3 cos 2 theta, and the IB part will equal 6i sine theta over the same denominator. We can cancel out these i's, so we'll get B as 6 sine theta over 5 minus 3 cos 2 theta. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the full lesson and the PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link below.